Carburetors are a lot like a puzzle. If you don't know how the pieces fit together, you'll never fully understand how it works. And that's what this session is all about. Taking the puzzle out of servicing the Mikuni carburetor by showing how each component functions, so you'll see the complete picture. The Mikuni carburetor is used on Aries, Reliant, Dodge 400, and LeBaron cars equipped with 2.6-liter engines. It's also standard on Challenger and Sapporo models, as well as the D50, D50 Power Ram, and Aero pickups. The Mikuni is similar to other carburetors used on 4-cylinder engines. There's both a primary and secondary barrel with throttle blades, a float assembly, needle valve and seat assembly, plus a bowl vent to control carburetor bowl vapors, and an accelerator pump system. The uniqueness of the Mikuni carburetor is in its additional control features. For example, it has a sub-EGR system to control the amount of exhaust gas recirculation, a jet air control valve to control the quantity of jet air metered into the cylinder, an idle-up system for K-cars with air conditioning, an idle fuel cutoff solenoid to prevent dieseling, a coasting air valve to reduce emissions during deceleration, and an air switching valve to improve fuel economy and reduce emissions during deceleration. Those are the basic components. Now, let's see how each functions. On the Mikuni, the secondary throttle is prevented from opening until the primary throttle is opened at least halfway. When activated, the vacuum control diaphragm opens the secondary throttle. A lack of acceleration or poor performance suggests a possible problem with the control diaphragm. The sub-EGR valve works in combined operation with the action of the primary throttle valve and controls the amount of EGR from both the primary and secondary EGR valves. The jet air control valve is actually an on-off valve that supplies additional air when the engine coolant is cold. It shuts off when the engine is at normal operating temperature. Both the air switching and coasting air valves are regulated by the air switching solenoid. When the engine is decelerating but is above 1800 RPM, the engine speed sensor closes the air solenoid. This activates a vacuum circuit, allowing the coasting air valve to supply additional air to the intake manifold and the air switching valve to cut off fuel flow at the bypass and pilot holes. Like any other carburetor, the fuel inlet system is designed to maintain a constant fuel level. Use of a filter screen above the float needle valve assembly is unique to the Mikuni. The idle and primary metering system consists of a primary main jet, primary pilot jet, idle mixture adjusting screw, primary main nozzle, and enrichment valve assembly. This system supplies mixture for idling, off-idle, and cruising at part throttle, as well as full throttle operation at lower engine speeds. Engine afterrun is prevented by an idle fuel cutoff solenoid. With the ignition switch off, the solenoid is deactivated, blocking the idle fuel circuit. The secondary metering system has a secondary main jet, secondary pilot jet, secondary main nozzle, plus a vacuum-controlled diaphragm. When power demand exceeds the primary barrel supply, the Venturi vacuum reacts against a spring force within the vacuum diaphragm to activate the secondary barrel. There's also a spring-loaded vacuum-actuated diaphragm enrichment system to provide additional fuel during heavy throttle conditions. With the engine running at part throttle, vacuum draws the diaphragm up against spring tension, closing the enrichment valve. Under heavy acceleration, the manifold vacuum drops, forcing the diaphragm downward, opening the enrichment valve. Mikuni carburetors utilize a conventional mechanical type accelerator pump consisting of a flexible diaphragm spring, lever, push rod, and follow-up spring. When the throttle is opened, the spring-loaded push rod compresses the diaphragm spring, forcing fuel up the vertical passage into the primary venturi. The automatic choke system is actuated by a thermal wax element connected to the engine coolant system. When coolant temperature is low, the choke valve is held in a closed position. As the coolant temperature increases, the thermal wax element expands, allowing the choke to open. Carburetor bowl vapors are controlled by a bowl vent valve. With the engine running, vacuum closes the valve. The solenoid then holds the valve in the closed position. Many of the circuits on the Mikuni are vacuum operated. So if you have a problem, visually inspect hoses first to make sure they're properly routed and connected, particularly if the carburetor has been serviced, because damaged or improperly installed hoses will cause a stalling or poor idling condition. It's important to understand when you have vacuum. With domestic carburetors, vacuum only goes to a component when that component is operating. Chrysler import carburetors have a continuous vacuum supply. When a component is not needed, vacuum is reduced by an air bleed. Hose inspection should include the dual solenoid valve hoses, connections at the main and damping canisters, and the vacuum advance hose at the distributor. Also, check the two thermal valves and both the primary and secondary EGR hoses. Remember, the coasting and air switching valves are controlled by the same vacuum source. Check the idle-up system hose connections and intake manifold vacuum connector located under the carburetor. Pay particular attention to hoses and nipples at the impact plate. They could be pinched or damaged. And remember to check all vacuum supply hoses for accessories, such as air conditioning or power brakes. Make sure all wiring is properly connected at the carburetor, alternator, and wiring harnesses. In addition, check all wires at the spark plugs, coil, and distributor cap. First, make sure idle speeds and timing are set to emissions-labeled specifications. Improper idle speed can be corrected by adjusting the curb idle speed adjusting screw. The first adjusting screw you see is for idle-up adjustment. But don't try to adjust it for curb idle, or this will happen. The curb idle speed adjusting screw actually sits at an angle. It should be set to emission-labeled specs. An idle-up adjustment screw is found on all 2.6-liter engines, but it's used only on vehicles with air conditioning and only operates with the air conditioner on. To make an idle-up adjustment, set the parking brake, put the transaxle in neutral, turn off all lights and accessories, and run the engine at idle. Then put the air conditioner in the max position at low blower speed. Make sure the compressor clutch is engaged during the adjustment. The idle-up system should raise the engine speed to 900 RPM. If the idle-up speed is off spec, Raise or lower engine RPM by adjusting the idle up screw. If your testing procedures leads you to an idle mixture adjustment, you should perform the following steps. Under current emission regulations, idle mixture screws must be sealed with a tamper-proof plug. So you'll have to take the carburetor off the car to remove this plug. If it has a roll pin, follow the service manual procedure. If the concealment plug on the Mikuni carburetor is hardened steel without a roll pin, remove it by first drilling a 3/32 inch pilot hole at a 45-degree angle behind the plug. Next, re-drill the hole with a 1/8 inch bit. Then drive out the concealment plug with a narrow pin punch and remove all metal chips with compressed air. At the engine, remove the impact plate and reinstall the carburetor to set the mixture. A new base gasket is required. But a word of caution. Don't use a Solex or pre-1981 gasket. Although the stud spacing is the same, 3 vacuum circuits will be exposed and cause leaks. Also, never use any sealer on a gasket. It will plug air passages. With the carburetor in place, make sure all vacuum and electrical connections are secure and clamp the pulse air feeder hose. The infrared emissions analyzer test is the only authorized adjustment procedure possible for checking proper idle mixture on 2.6-liter domestics and imports. Be sure that both the curb idle and basic timing are set to emission label specs. Provisions for propaning are not available on Mikuni carburetors. Incidentally, don't adjust any screw sealed with white paint. It's calibrated at the factory. After the mixture adjustment, reinstall the concealment plug and impact plate. Don't forget to remove the clamp on the pulse air feeder hose. Due to their wide tolerance, float level is rarely a problem with the Mikuni carburetor. So adding or subtracting shims is seldom required. But if it should become necessary to adjust the float level, always maintain a right-angle relationship between the needle valve and float arm. Never bend the float lever. It could result in fuel starvation. If your diagnosis requires component replacement, use an impact screwdriver to break the screw loose. Be sure to use a Phillips bit that fits snugly into the screw head. With this method, you can easily remove the screw along with the component. Checks and adjustments for the 2.0 and 2.6-liter Mikuni import are much the same as for the carburetor on domestic models. Once again, inspect all hoses to see if they're properly connected. Also, check hose routing labels. Imports have the same adjustment screws, including the curb idle speed screw, idle up adjustment screw for vehicles equipped with air conditioning, and a mixture adjustment screw. But there are important differences. As mentioned earlier, domestic cars equipped with air conditioning have only one idle up adjusting screw. But imports equipped with air conditioning and manual transmissions have 2 adjusting screws. Here's the primary idle up adjustment procedure for imports. With the engine running at normal operating temperature, shut off all lights and accessories. Place the transmission in neutral and set the parking brake. Make sure curb idle speed is within the specified value on the underhood emissions label. If necessary, reset the curb idle speed by readjusting speed adjusting screw number 1. Then, switch the air conditioner on. Put the blower at low speed and adjust the idle up RPM to specified value with the throttle opener setting screw. Next, verify proper idle up system operation. If this primary adjustment procedure doesn't provide proper idle up specifications, check the Technical Service Bulletin dated May 4th, 1981 for the alternate procedure. It covers speed adjusting screw number 2, which is for a much finer idle up adjustment. Whether it's an import or domestic, it's important to understand how all the pieces fit together. It's also important to inspect all vacuum hoses and wiring to see that they're correctly routed and connected. If you know the proper location of adjustment screws and follow critical procedures and specs, servicing a Mikuni carburetor is really not so puzzling after all. Get the picture?
The Mitsubishi 2.6-liter EGR system components are somewhat different than the domestic EGR system components, but the basic operation and drivability related complaints are very much the same. In order to meet the non-standard, increased EGR flow is required, but this directly affects drivability. To solve this problem, a dual EGR valve is used in series with a sub-EGR valve. The dual EGR valve consists of a primary and a secondary valve made together as one assembly, but each diaphragm is controlled by a different carburetor vacuum signal in response to the throttle valve opening. The primary valve controls EGR flow when the vehicle is operated with a narrow throttle opening, while the secondary control valve allows more recirculation of exhaust gas when the throttle valve is open wider. The vacuum applied to the dual EGR valve is controlled by two thermo valves. The thermo valves are used as a metering device to bleed off a vacuum circuit. Notice that each valve has an external vent. The lower valve, located in the block below the thermostat housing, is thermo valve A. The external vent is located on the side of the valve. The vacuum from the carburetor to the primary EGR valve is vented to the atmosphere through thermo valve A when the engine is cold, thus preventing any primary EGR valve operation with a cold engine. As the engine warms up, thermo valve A closes off the vent to the atmosphere, which allows the vacuum to build up and operate the primary EGR valve as the throttle is opened. Thermo valve C is located higher in the block and to the right of thermo valve A, as viewed from the front of the engine. The external vent for thermo valve C is located on the end. Thermo valve C controls the operation of the secondary EGR valve. Again, when the engine is cold, the vacuum signal from the carburetor to the secondary EGR valve is vented to the atmosphere through thermo valve C, preventing any EGR valve operation with a cold engine. The sub-EGR control valve is located in the throttle body of the carburetor and is connected to the throttle shaft by linkage. When the throttle is closed to normal curb idle, there should be no EGR operation regardless of engine temperature. This means that the outlet ports for both the primary and secondary EGR valves must pass through the sub-EGR valve. As the throttle valve opens the sub-EGR control valve, exhaust gases are allowed to enter the intake manifold. This system allows the control of EGR operation by vacuum as well as by throttle response. thereby giving a smoother flow of exhaust gases throughout the entire operating range, which improves vehicle drivability. Remember, customer satisfaction can be obtained by understanding of the EGR system. Next month, we will continue our coverage of the 2.6-liter Mitsubishi EGR system with component testing. Plan to be with us.
For the past year and a half, I've been able to go through the technical highlights with you in the MTSC sessions, and I've really found it an enjoyable experience. I hope that you have found it as such. In the past couple of months, I've assumed some new responsibilities here at the Service and Parts Operations Group, and this will be really the last session that I'll be talking to you during the MTSC technical trailer. I'd like to take this opportunity to thank you for all the time you've spent going through these sessions, and I'm sure you'll continue to do so. You'll see a new face starting with this month's presentation, one that I'm sure you're going to enjoy. So at this time, I'd like to introduce to you Mr. Ray Stone, our new Manager of Service Engineering.
You may encounter an oil leak at the rear of the intake manifold on 318, 360 engines. The cause of this oil leak is due to a slippage of the gasket between the intake manifold and the engine block. For demonstration purposes, we have simulated the gasket slippage on this engine to show you the condition. You can repair this leak without removing the intake manifold. The procedure is as follows. After removing the air cleaner as well as any other components to gain access to the rear of the intake manifold, remove the oil pressure switch and plug the hole with a 1/8 inch pipe plug to prevent contamination. Next, use an X-Acto knife or a single-edge razor blade to cut the blown-out portion of the gasket flush with the manifold. Clean all dirt and grease from the area to be repaired with Mopar brake and carburetor cleaner. Then, put a bead of RTV sealer along the affected area. Use your finger to force the sealer between the manifold and the block. Now, remove the plug you installed in the oil pressure switch hole. Place an intake manifold gasket retainer behind the sealer with the recess lined up with the oil pressure switch hole. This is done to hold the RTV sealer in place. This gasket retainer, part number 4105671, is available from your parts depot. Place a drop of Mopar Teflon thread sealant on the oil pressure switch threads and install the switch. Reinstall the vacuum amplifier and any other components that you had to remove to gain access to the manifold. Refer to Service Bulletin number 090482 for details on the repair of the intake manifold gasket. Should you have to make any other repairs which require the removal of the intake gaskets, you should also be aware that both the procedure and the end gaskets have been changed. The procedure has been changed as follows. After the intake manifold and the old gasket material are removed, clean the cylinder block front and rear gasket surfaces using a suitable solvent. When installing the composition gaskets, keep them in place with the plastic gasket retainers supplied in the gasket package. Do not use sealer on the side gaskets. Install the new plastic guide pins in the front and rear gasket rails to position the gasket on the block. Next, apply a thin, uniform coating of a quick-dry cement to the front and rear gaskets and cylinder block gasket surfaces. Allow the sealer to dry until tack-free. Carefully install the end gaskets. Bend the tabs on the head gaskets down to retain the gaskets. Place a bead approximately 1/4 inch in diameter of RTV sealer at each of the 4 points where the end gaskets meet the side gaskets. Finally, install the manifold and torque the screws to 40 foot-pounds. This concludes our session on 318-360 engine intake manifold gasket repairs. Thank you for your time. I'm looking forward to talking to you at our next session.